Our next talk is going to be by Thomas, and he's going to tell us about how to compile separation logic to linear hardware capabilities such that the result can be safely composed with untrusted code. Take it away.
Yeah. Hi, everyone. As Ralph said, I'm going to talk to you about the use of linear capabilities to fully abstractly compile separation logic verified code. Now, let's first take a step back and have a look at the problem we're trying to solve here. So separation logic is used in a lot of verification tools to achieve sound and modular verification. And this also means we can take some verified code, we can take some code, verify it, and put it in an untrusted, unverified context. Now the problem here is that if we do this, then actually the static separation logic guarantees that we had at compile time are now lost at runtime. And in this talk, I'm going to propose a solution where we actually securely compile the verified component in such a way that separation logic guarantees are, in fact, upheld at runtime. So an outline of the presentation. First, I'm going to present a running example. Then I'm going to talk about and verify it. Then I'm going to talk about why separation logic guarantees are not upheld at runtime, given this example. Then we're going to compile the example in a secure way and make sure that separation logic guarantees are now upheld at runtime. Then we're going to talk about what we mean exactly by this notion of secure compilation, which will come down to full abstraction in our case, and why we want full abstraction. And then I'll conclude and quickly discuss some future work. So our motivating example, it looks as follows. We have a source component, which consists of a function f, and we have an untrusted, unverified context function, which is just supposed to be an identity function. So let's quickly have a look at what this function f does. It accepts an integer pointer a, and in our case, we conflate the notion of pointers and arrays in this talk, just for simplicity reasons. It passes this a to an identity function, so nothing should happen to it, and then it mutates the first element of this integer array a to sets it to 1. Now, as I mentioned in the title, we're going to have a look at separation logic verified code, so we will need to verify this function f, of course. Before we can get into the verification, we need to introduce a couple of notations. So this is called a points to chunk, and it's used to denote a permission to access the heap. So in this case, this denotes a permission n to access the array with elements C1 up to Cn, starting at memory location A. A second notation is the asterisk, the well-known separating conjunction, which denotes spatial separation in the heap. So this denotes two permissions n and m that are spatially separated. Before we can make a separation logic proof of our example, we need to annotate the functions in our example, f and id, with a separation logic contract first. So let's have a look at what this kind of contract might look like. So in this case, our function f accepts a resource n to access the singleton array 0 at location A, and it returns this same permission, now under the name m, to access a singleton array, the same singleton array, but now with contents 1. And as expected, the identity function just accepts the resource n in its precondition and returns the same resource m, so it, as expected from an identity function, it doesn't do anything to this resource. By the way, the reason we name these resources is because we need those names in the compilation later on. So now that we have our separation logic contracts, we need to actually construct separation logic proofs from these contracts, which take the form of Hoare logic proofs that say that if we have the precondition of our function and we have the function's body, then we can derive the postcondition. So in the case of f, this will be a really easy proof. We start from the precondition, we expand it. This exactly matches the precondition of the identity function, so we consume this, and we get back the postcondition here. And then we have our array mutation. So what this does is this just sets this 0 to 1 in the permission in the resource corresponding to the variable a, and we've arrived at the postcondition. So we now have a verified example, and we can take a look at what goes wrong at runtime. Before I get there, though, one important observation we need to make is that, which is important for this talk at least, is that separation logic resources behave linearly. Now, what do I mean by this? If we take a look at the call we had on the function call we had on our previous slide here, we can see that the resource n is consumed by the call to the identity function because it appears in its precondition, and then after it's produced again. We also, at the source level, to give another example of linearity, we have a split ghost command, which operates on logical state, which takes a resource n and splits it into two adjacent resources n1 and n2, in this case at index 1. Dually, we also have a join ghost command, which takes two resources and linearly combines them into one. So why are guarantees not upheld in this scenario? We'll talk a little bit about that. But essentially, the problem is if we take f and we link it with an implementation of the identity function, at runtime we just erase all the separation logic information we have, and we have no guarantees that ID effectively upholds its contract at runtime, because it's both untrusted and unverified. This means that the identity function can do three different things that we don't want it to be able to do, given its contract here. The first thing is that it can read or write outside of the bounds of A. So for example, it's only allowed to access one element at memory location A, but here it could just write at index 1 instead of at index 0, which we don't want to happen. It could also just make a copy of A, store it in a global variable for later use, even though it's supposed in its post condition to return a permission to access A, so it cannot make a copy and store it. And it could also just generally not satisfy its post condition by, for example, setting the one element of A it's allowed to access to 2 instead of keeping it at 0. So to kind of reiterate, we have regular verified C code. We want to do better than just erasing contracts. We want to securely compile it. And to do this, we're going to need some kind of language enhancements in the target language that we're going to compile to. And now the question is, what are the language enhancements that we need in this case? So we're going to have a look at each of these three problems and see how we can fix them. So first of all, the out-of-bounds reading and writing we can fix by using a notion called capabilities, which is a special type of unforgeable memory pointer that grants a set of permissions on a specific region in memory. And in our case, these will just always be read-write permissions, but in general, they could be other permissions as well. And they make sure we have a kind of hardware-enforced fine-grained memory protection. And you can see them, in our case, as a type of bounds check pointers, but hardware enforced. So for example, if this A were to be a capability, then this would not be possible, because ID could only use our bound check capability to access the first element of A. To avoid copying and storing A, we introduce a special type of capability called a linear capability that prevents duplication. So what this means, linear capabilities are non-duplicable. What this means is that if we have a linear capability valued variable in the stack, for example, and we use it in one of these statements, we execute those statements, then after they are executed, this variable will be set to null in the stack to avoid, because otherwise we would be taking a copy of the capability. The other way around, if we use this value twice, our code will just get stuck in execution, because otherwise, again, we would have duplicated our capability value. So the consequence of this is that we know that an untrusted party, if we possess the linear capability, could not have kept a copy. So in this case, after our call to the ID function, we could check that we actually possess the linear capability A, and then we would know for a fact that ID could not have kept a copy of it. And thirdly, to make sure that stuff like this doesn't happen, we are going to wrap untrusted functions such as ID in checking functions, also called stubs, which just check their post condition. To reiterate and kind of already give a sneak peek into the intuitions behind our compiler, this is our setting. So we have our verified C code with linear resources, and we have our unverified target language code with support for capabilities which are, again, linear. And this parallelism between the two notions of linearity is kind of one of the main intuitions behind our compiler. So let's now have a look at how we're going to compile the example. As we said before, and let's just start by the intuition behind the compiler. As we said before, the resources, separation logic resources we have, they behave linearly. And they contain all the permissions to access the heap. So it makes sense to reify this resource M we have here, to reify it into a linear capability M that also represents permissions to access a heap. Now, on the other hand, the original pointers we have in our source program, such as the integer pointer A, they do not really represent permissions, because we cannot use them to access the heap in a separation logic proof if we do not also have this resource M. So we can just safely compile them down to regular integer pointers. And we keep those for just regular address arithmetic and stuff relating to addresses. So that's the intuition behind our compiler. We're going to reify resources. But how are we going to use these resources in a compiled program? Well, we say that our compiler is separation logic proof directed because it doesn't just take the source code as an input to our compiler, but it actually takes the separation logic proof of the source code to guide compilation. And concretely, the main intuition is that we're going to compile operations on resources to manipulations on the corresponding linear capabilities. So let's see an example of this. For example, in this array access we had in our array mutation, we had in our example, we can see that the resource M is being manipulated by this access, and so we're going to compile this down to a manipulation and the corresponding manipulation setting the first element of the corresponding linear capability to 1. Another example is with the split ghost command. We're going to compile this down to, we're going to create a built-in target function called split, which splits the corresponding linear capability at the same index here. So the idea of our compiler, to reiterate, is to compile operations on separation logic resources down to corresponding operations on linear capabilities. So then we're finally ready to compile, to look at the compilation of our entire example. As I mentioned, our compiler is separation logic proof directed. So this means we take this proof of F's contract and not just the code of F itself as input. Let's first have a look at what happens to F's declaration during compilation. And we can see that F takes resource N as an input here and outputs the resource M. And since these two resources are reified during compilation, we can see that we get an extra argument N here, and we get an extra return value, returned linear capability M, and an extra return type here. And this A from here just becomes a regular integer. And the same thing happens to the declaration of the identity function. So secondly, if we look at the call to the identity function, we see that we consume a resource N, we produce a resource M here, and we see that the same happens in our code here, where we, instead of directly calling the identity function, we actually call the function ID stop instead. And I'll talk a bit more about this wrapper function on the next slide. Then this one we had before. So we can see that because we hand the linear capability to the identity function, we actually force it to perform all its memory accesses through this linear capability, and we know that overreads, overwrites, and the copy problem that we had before, that they cannot occur. And to enforce the post condition of the identity function, we create a stop function or a wrapper function around this identity function that checks that the post condition of this ID function is actually being upheld. So these 4 guard statements are just sort of verification of all the implicit restrictions present in this post condition. Okay, before last section, we talked about security and about wanting to securely compile separation logic verified code. And now I'm going to instantiate our notion of security by full abstraction, and I'm going to talk about why we want full abstraction and why it's useful in this context. So what is full abstraction? Full abstraction is a very general notion with which we can instantiate secure compilation. And intuitively, it says that it's as hard to attack compiled code as it is to attack the original source code. And that's very interesting in our case, because it means that even if no verification is present, even after we've compiled our source code, it's as hard to attack our now non-verified code as it is to attack our original code. So that effectively that means that even without separation logic verification, we know that separation logic guarantees are being upheld at runtime. Slightly more formally, full abstraction is also defined in terms of reflection and preservation of what we could intuitively call attackability. So if we have 2 source components S and S prime, and there exists an attack that distinguishes these 2, there should exist an attack on these 2 if and only if there exists an attack on their compiled versions. And usually full abstraction is split into 2 directions, a correctness and a security direction. The first one is correctness, which states that if there is, it's kind of like a sanity check on your compiler. It states that if there is an attack on the source level, there should also be an attack on the target level, and we can just prove this using our compiler. Now, for the opposite direction, which is called security, This states that if there is an attack on code in the target language, there should have already been an attack in the source language, which is exactly where this intuition comes from. And here we need to introduce a new type of translation, kind of an opposite direction compilation, which is called the back translation. And what the back translation does is it tries to mimic target behavior in the target code behavior in the source language. And in our case, we use a sort of free contract approach, which is very similar to the well-known technique of universal embedding from full abstraction proofs. We use this type of technique to construct our back translation. So to conclude and discuss a tiny bit of future work, what I did here was I presented a compiler from a verified source language, verified C-like source language with separation logic annotations. I compiled and to a target language, which is regular unverified C code with support for linear capabilities and also linear capabilities, very importantly. And we proved that this compiler was fully abstract. And by proving that this compiler is fully abstract, what we're doing is we're effectively proving that any static separation logic verification guarantees we had at compile time are actually being upheld at runtime. And a tiny peek into future work before my time runs out. There's three main things I wanted to mention here. We think that a lot of what we did can also be applied to substructural type systems, and we could probably use Rust as a source language instead of what we did here, because ownership and mooring have some linear aspects to them. A second thing we want to achieve still is we want to support gradual verification, because one problem we have here is that if we compile this function f from our example down, its declaration changed. So that makes it impossible to link to other original source code. We want to fix this. And a third thing that we think we can reasonably easily do is extend our source logic to support a general type of abstract predicates to, for example, support lists. And then we would need to add probably add sealed capabilities to the target language instead. Okay, thank you for your attention.
Okay, where we get the mic there, we'll start with a question from Slido. Why is a pointer translated to a pair of a pointer and a capability? Isn't the capability alone sufficient?
So pointers aren't being translated to pairs of pointers and capabilities. Pointers from the source language are being translated to addresses, and the resources from the separation logic are the things that are being translated to linear capabilities. And the reason we keep these separated is because of aliasing. So if you have multiple versions of a pointer in a source language, and you only have one resource for all those pointers, you can't just throw away the source language pointers, because they could have different addresses, and we would lose this information during compilation.
Hi, sorry, my voice is slightly working. In the motivation you gave, you mentioned that when you're linking, like when you have a declaration of something in your context and you're linking against implementation, you're not sure what it might do.
Mm-hmm.
Like the example you gave, you changed the interface of the external function.
Mm-hmm.
You changed the return type, but you added an additional argument. This means that you need to have a specific way
Mm-hmm.
to use externally defined functions in your system. Is that true?
Yeah, so that's what I meant by gradual verification. So at the moment, we're having the problem that our approach actually changes declarations of functions. So we can only link against target code that, let's say, supports our calling convention.
No, but okay. So when you say F here, that means also ID there, right?
Yeah, it also means that the declaration of the call to ID, as you say, will be changed, and that also means that we can only link against ID functions that respect our new calling convention.
Okay.
But they can do whatever they want. They don't need to uphold their contract, but they still need to respect the calling convention. So that's a limitation, and that's one we're wanting to lift.
Okay, thanks for clarifying.
Another question from Slido. Your compiler appears to compile statically verified code to code with dynamic checks.
Mm-hmm.
Why introduce dynamic checks into verified code?
So that's definitely partly true. I would say because in this setting at least, there's no other way to make sure that the things like the identity function actually uphold their post condition.
But I guess you could imagine inside the verified code, which trusts itself, right?
There are no dynamic checks inside verified code.
Okay.
But on trust boundaries, you kind of need to have them. But you could kind of see our compiler as two separate things. So on the one hand, it employs linear capabilities to, in a way, avoid dynamic checks, because the dynamic checks happen in the hardware. And on the other hand, we actually use dynamic checks for the things that linear capabilities can check, which is basically for things that aren't the framing rule in separation logic, sort of. And so we do avoid some dynamic checks using linear capabilities, but we can't avoid them all. It's basically the point, I think.
I was wondering how untrusted is this untrusted code? Because, like, I mean, you checked some properties of the identity function here, but in principle, this identity function could write to anywhere in memory, or like, is there an implicit frame condition, and how do you check that?
It can't do that because we use capabilities. So it can only, like as I say in the capability world, connection begets connectivity begets connectivity. So it can only use the capabilities we give it and the capabilities that it gets from somewhere else to read and write to code. So it can't just check anywhere in memory. Because we're working in the setting of a capability machine and not a regular, not regular hardware.
Question from Slido. The precondition a maps to 0 is very constrained for an identity function. Could you generalize that to like any value, any input array, something like that?
We do have some. This is definitely like I kept it simple just for the sake of the illustrative example. And we could generalize it because we have in the paper we have resources that allow nested and unknown length arrays, but we still have some restriction on what we call boundary functions, which are the functions at the trust boundaries. So in our current setting, we couldn't generalize it to that, but I think it should be reasonably simple to extend our proof to actually make that happen.
Okay. Can I take one last question while the next speaker is setting up? Something from here. So we have something from Slido. How is the performance penalty due to the extra checks?
That's a good question, and also one that's pretty hard to check. We thought about checking it, but the problem is there's currently no implementation of linear capabilities that we could use in a capability machine. So we would need to emulate them on something like QEMU or something of the sort. And then see what the penalty is, but then the question is, what are we going to compare it to? Because we will incur some slowdown from emulation itself also. So we haven't tested yet.
Okay, thank you.